So can you hear me well there? Good. So let me thank the organizers for the invitation. So I don't see that many of the organizers are around, but especially Hal for having me here. It's great to be back in India. So this talk is, the plan is to have a very introductory talk on integrability and what happens when you take systems that are integrable out of equilibrium. So I will touch upon things that have been said, or were said yesterday. And I hope this is going to be useful then later for you, for all the talks that will deal with generalized hydrodynamics and so on. So, okay, so this is the plan. So I have a long introduction. And then I want to tell you 3 things about integrable systems. And I would like to get as much, as many questions as you feel like asking. So it doesn't matter where we stop. These are pretty independent things. So we can really stop before we make it to the end. Okay, so let me start with the experiment. So why is it that we've been thinking about integrability in recent years in the context of systems far from equilibrium? It's really mainly motivated by experiments, and then we've realized that there are many interesting questions to be addressed there. So the experiments I have in mind, and because integrability is very much restricted to one dimension when you have interactions, are experiments in one dimension. So you can ask yourself, oh, how do they get one dimension in a lab? So there are various ways. So the one I probably like the most, because it's very close to my office, is using optical lattices. So what they do is they trap Bose-Einstein condensates. They cool them down in 3-dimensional traps. So now you have a 3-dimensional gas. And what they do is they load them in a 2-dimensional optical lattice. So there is some detuning of these lattices to atomic resonances, and depending on the detuning, the atoms are either attracted or repelled from the maxima of the interference pattern, and then you can have these very tight bosons in one dimension, and then you will have an array of them. Okay, so what's great about these? These are very cold. So in 3D, you can describe interactions to be contact interactions, but then even if you go to 1D, and that was something that was done by Maximo Chane, you see, 20 years ago, you find that the effective interaction of those bosons are contact. And the great thing is that now you can control how strong this is by just changing essentially the intensity of the laser will control this omega perp. Okay, this AS is this scattering length in 3 dimensions. So you see, you can control interaction in here by just controlling how intense your lasers are to create this one dimension. So, and then if you have bosons in one dimension, so you probably have heard about, they are essentially described with contact interaction by this Lieb-Liniger model, which is an exactly solvable model. It was introduced in 63 and solved by Lieb and Liniger, and it has a very interesting limit when this G1D is infinity, and that's the Thom-Girardot gas, or the Girardot limit, which is then even simpler. You can solve it by mapping it to a non-interacting fermions, and I'm going to be using this mapping in this lecture. Okay, so then what I'm telling you is these experiments are like an ideal realization of these models. So let me show you how ideal this is. So these are results obtained in the group of Dave Weiss there at Penn State. And what is plotted here is really this G2 correlator. So that's a local correlator, which he can measure using photoassociation, right? It's kind of amazing that he can measure this object. And then it's plotted here as a function of this gamma effective. So gamma in the Lieb-Liniger model is what controls everything. So everything is parameterized, you see, as a ratio of G, which is this thing in here, and the density. Okay? So now you see they can change the density by changing the number of atoms that they load in the tubes. And though they can change, now you see they can change gamma by changing the lattice depth and by changing n. And that's why there are different set of data. You see green and so on. So essentially, they change the number of atoms, then change the lattice depth, and so on. And what happens as you increase gamma, you go to this gamma infinity, you go to this Thom-Girardot limit where this correlator should be 0 as for free fermions. And now the points are the experimental data. The line is essentially linear theory within local density approximation, because in those gases, they are not homogeneous, so they have a trap. So you see, they don't extend forever, and it's not periodic. So you have to use the local density approximation. So the density changes. They are into a very good approximation in a confining harmonic potential. Okay. So here you see that's now the continuum model. So the other thing that you can do in these experiments is add a lattice along this direction, a weaker lattice, so that the bosons can hop around in that lattice. They still don't move between tubes, but they hop in that lattice. And that, in the limit of very strong repulsion, is another model, exactly solvable model in lattice systems, and essentially the XX model. And that was realized in the group of Immanuel Bloch, you see, around the same time. And these two plots somehow help you have an idea of what the experimental setup looks like. So you see, this is what I was telling you, that there is a trap. This is the lattice along one dimension, and this is the density of the distribution of the particles. Okay, and you see that because of the confining potential, then it's inhomogeneous. And now what they can do is they can do time of flight measurements, and I'm going to be talking a bit more about that, and measure the momentum distribution function of the gas. And here you have the dots are the experimental measurements, and then the line is just the theory considering infinite repulsion. So you see how well this fits there. Not quite quantum dot, because this is 1D, and then along this line you have the lattice sides, and you move between the sides. Okay, so they are free to move along the sides. So, and that's why the dynamics here is one-dimensional. Okay, so that's great. So you see the equilibrium is somehow very well controlled. And now what you can do is, it's amazing in these systems, is you can take them out of equilibrium. Okay, so which is kind of tough if you have a condensed matter setup where time scales are very short. Okay, and this is somehow what started it all. Okay, so that essentially Dave Weiss, in this paper, so he essentially got his bosons. So this is a sort of, I'm going to show you like a numerical experiment that is similar to what he did. I mean, he did something that was nicer than what I'm going to show you, and you will see why. But this really makes the point. So they have these atoms in the trap. So this is the density distribution. So at very low energies in momentum space, that's the momentum distribution. So right, you remember that bosons, they like to condense, but in one dimension they cannot condense. So, but they still have some divergent zero momentum peak. Okay, does everyone understand that initial state? So if you would be in higher dimensions, this would be a Bose-Einstein condensate. In one dimension, it's really like a quasi-condensate. So, and then what Dave did is he pulsed lasers, like 2 pulses, and then split so you see everything that was at zero momentum is gone, and now he moved everything from there to some finite momentum, and these peaks are commensurate with the momentum of this lattice that he had. So, and then he let it evolve. These dynamics I'm going to show you is exactly the Tongue-Girardot limit. So I'm solving it exactly, and I'm going to show you how I solve it. But this is exactly what I did. So I got this initial thing, and then I pulsed a lattice, and I created a state that the density looks like this, and the momentum didn't quite look like this. It had an extra peaking here. Okay, but in his experiment, it looks like this. The density will look like this, and the momentum looks like 2 peaks. Okay, so other questions? So good. So let me show you what happens. Okay, now this is the exact numerical simulation of this Tongue-Girardot limit. I'm going to tell you later how this is done. Okay, so something is happened. So let me see. Okay, that's bad. So, oh, you see it in there. Okay, so let's see. See if I do it again. Okay, good. So coming back. So this is what happens. Okay, so remember I started from a state in which everything was in here, and you had 3 momentum peaks. And you know, if you let that guy evolve, what you see in this is in the numerical simulation is in a perfect harmonic trap. And what you see just go back and forth. Okay? So, and that's pretty amazing, right? Because you have those bosons, you have hundreds, thousands of collisions, and they just go back and forth. They don't equilibrate. Okay, so let me show you, and that's why this is being called the quantum Newton's cradle. So that's the way this experiment is known, because you see you have this bunch of atoms, and it's very similar to what happened with this classical toy, where now you think of these as the bunch of atoms that are moving out, in and out. So in the experiment, so this is how things look like, and that's why I was telling you in the theory, you see I didn't remove the 0 momentum peak, so in the theory I always have the momentum peak, but the fissures are there. Okay, so they go back and forth. Now, of course, the experiments are not a perfect harmonic oscillator, like a perfect harmonic trap, and then the tubes are different number of particles. So really, they can see what I see in the theory for a few periods, maybe a couple of periods, and after some time, what they see is that the momentum distribution function doesn't change. Okay, so and this is how that momentum distribution function look like for different values of gamma. Okay, I told you that they can change that gamma, in particular here, they change it by changing the number of atoms. Okay, so this is like kind of the equilibrated result that they get, okay, for different gammas. And now what is remarkable about this result is that, you see, you will never get a momentum distribution function that looks like this if you do statistical mechanics in harmonic trap. Okay, so this is something that you cannot describe using statistical mechanics. Somehow the system is remembering that initial state in which it had the kicks. So, and as you reduce gamma, I mean, those peaks are watched out, but you see the lowest gamma that they could go, still the momentum distribution function, which is this, didn't look quite like the thermal distribution that you would expect. Okay, so as far as they could go, so they didn't see statistical mechanics. Okay, now you could ask, so why is it that they don't go to lower gamma? Because to reduce gamma, they have to increase the number of atoms or decrease the lattice depth, and then what starts happening is that you start hopping out of the tubes, and then the system becomes effectively two-dimensional. Okay, so this is the regime in which they can keep it strictly one-dimensional for the time scales they have. Okay, and this is the kind of thing that we are going to be discussing in this lecture. Okay, so any question about the experiment? Right, I mean, the trap indeed, it breaks integrability, but it's weakly enough that you don't see it in the time scales of the experiments. It will, yeah, it will probably go. But you probably thermalize not because of the trap, but by other processes that are even faster than that. Okay? So now, right, to move forward, then I have to tell you what is special about this and what is special about integrability. Okay, and for that it's good to go back to classical mechanics, and I think you saw already these billiards yesterday. So essentially, if you construct some billiard, in general you do some, like in the computer, something that random billiard, you will get something that if you throw a particle after a few bounces, things are going to look like this. Okay, that's what you expect in general. Okay, and that would be chaos. So that's the typical thing, and essentially what chaos tells you is that if you change a little bit, right, the angle at which you shoot the particle, very quickly, one particle is over here and the other one is in whichever other place, like almost uncorrelated. But there are systems that are very different from that, and those are integrable systems. Okay, so what is special about integrable systems, and this is a very well-defined concept in classical mechanics, is that they have as many constant of the motion, independent constant of the motion, as degrees of freedom. Okay, so what does that mean? So this is the statement, so right, we can always write this as a coordinates and momentum. We have n degrees of freedom, and if you have n independent, and the statement is you have n independent constant of the motion in involution, so essentially you see they commute, Poisson commute with the Hamiltonian between themselves, and this is just to remind you what that means. Then there is this theorem, Liouville's integrability theorem, that tells you that there is a canonical transformation from the P's and the Q's to action angle variables, and the Hamiltonian then takes this form. And then you see that the equation of motion in these action angle variables are trivial. So the I's are obviously conserved, and then the angles are just having a trivial evolution. Okay, and that's what people think about evolution in a tori. Okay, so now how do we go from there to quantum? That is a tough problem, and I think people are still discussing what quantum integrability means, because you can see many issues with here, like, well, what are the degrees of freedom in the quantum case? If you change the I's by operators, what would independence mean in this concept for operators that commute and so on? So I'm not going to go into that. So what I'm going to do is I'm just going to give you like a picture of what, how you could think about integrability, and then like a prescription of how you could test it, okay? So the pictures go through this scattering without diffraction, which I learned some time ago, actually when I was a postdoc at UC Davis, and Rajiv is over there, so reading this book. So how is it that, what does it mean that integrable systems have like a scattering without diffraction? So suppose you have one particle in a well-defined momentum, so you have momentum, energy, and then you have your wave function, a plane wave. Another way you ask, the question that you ask is, what happens when two particles scatter? Okay, so they have the same masses, and so what happens when they scatter? So, and you see, because of momentum and energy conservation, then you immediately see that whatever momenta go in, they must go out. Okay, so, and this is what you think of in one dimension. Two body collisions cannot produce thermalization because of this, right? You cannot rearrange the momenta. Okay, so that's trivial. That will happen for all one-dimensional systems, no matter the interactions. So non-trivial things happen when you get more than two particles. So let's say three particles. And here the problem is that once in a while you're going to get these three particles to come by, close by, that they all interact. And now your energy and momentum conservation, they don't restrict the outcome of the possible momenta, right? So what does that tell you? That, well, possible momenta are the incoming ones and then gazillions of other ones. And those are the ones that are going to produce thermalization, right? So, and this is what is called diffractive scattering. So in integrable systems, something wonderful happens, and it's just those terms are not there. Okay, the interactions are such that you shoot three particles, they go out with the same incoming momenta that they had. You shoot four, again, all go out with the same incoming momenta. Okay, so that is this picture of scattering without diffraction. Now, this picture generated some confusion because you see this is like a zero density limit picture, right? 4 particles, 5 particles. So from this picture, you may erroneously conclude that if you have a Bose gas that is integrable, the momentum distribution function will never change. But if you are at finite density, what happens is that what are conserved are not the distribution of momenta, is something else, a distribution of rapidities, and those are more complicated things. So essentially, just be aware that there is a scattering of quasi-particles, and incoming rapidities are going to be the same as the outgoing, but those are not the momenta, the real momenta of the particles. And I'm going to show you that, okay? So those rapidities are the real momenta of the particles at zero density. And I will show you some very striking experiments showing that. Okay, is it clear? So think about it. At zero density, you have 1, 2, whatever. So you will get the same outgoing momenta that you had incoming ones. So if you are at finite density, it's something else, but there is something conserved. Okay? So, okay, that's good. That's the picture. So you see something that doesn't allow the system quite to thermalize. So, but if someone gives you a model, how do you know that the model is integrable? So this goes through a lot of work on in the field of quantum chaos and single particle chaos. And this goes through two conjectures, right? I come from these semi-classical limits. And the first conjecture is by Berry and Tower. So what they said is that if you have essentially a quantum system whose classical counterpart is integrable, then what happens if you look at the level spacing distribution at high energies, you are going to find that is Poisson distribution. Okay, so I'm telling you, so if someone gives you an integrable system, you look at the level spacing distribution, the expectation is if you have a classical counterpart, you are going to have this Poisson distribution. So if you have a typical chaotic or quantum chaotic system, then the distribution is completely different, and it's this BGS conjecture that at high energies, the distribution is going to be Wigner-Dyson distribution. Okay, and that goes back to work by Wigner and Dyson thinking about nuclear physics. And there is a universal distribution that comes out of random matrix theory. Okay, how well does that work? So now these are two billiards. So this is a rectangular billiard, and you see at high energies and just beautiful Poisson. And if you have this chaotic billiard, you have this beautiful Wigner-Dyson distribution, right? You see, this distribution is really non-trivial because it tells you that you have level repulsion. So the levels, you don't have levels very close to each other. Okay, but I mean, all this was done in this context of semi-classical limits, and you have counterparts that are either integrable or non-integrable. So, of course, we are going to be interested in many models which don't have a classical counterpart, at least in the regimes that we are interested in. And in this series of lectures, I'm going to be talking a lot about this kind of models. So these are one-dimensional lattice models, okay, in which you can put either bosons or hardcore bosons or fermions or spins, okay, and then let's think about it in fermionic language. So because we are going to be looking at fermions later. So what does this tell us? So these are models in which you have hopping of fermions between nearest neighbor sites and interactions between nearest neighbor sites. So these are spinless fermions. And then next nearest neighbor hopping and interactions. Okay? So now you'd say, why are you writing something that is so long? It turns out that this part is integrable, okay? This you can map into the spin 1/2 XXN model, so it's not to be quantum integrable. So if you look at now the level spacing distribution of these Hamiltonians, so let's say you fix some system size, 24 sites, that's about what we can fully diagonalize. You take 24 sites, and now you look the level spacing for different values of this T prime, B prime. So T prime, B prime, 0, perfect Poisson distribution, right? So sufficiently large, perfect Wigner-Dyson distribution, and then intermediate, you have something in between. And the important thing about that something in between is that it's moving to smaller values of this T prime and B prime as you increase the system size, okay? So essentially in the thermodynamic limit, the expectation is that any non-zero T prime, B prime will give you the Wigner-Dyson distribution. And this is what is shown in this plot. So what I have taken is what is this maximum, right, in the numerical result, right? And I have plotted as a function of this T prime, B prime for different system size. And this omega max in here is what random metric theory predicts. And you see what happens. So small system sizes, it takes very large T prime, B prime to get to this omega max. But as you increase system size, and you see the change is not that much, but you clearly see this moving in. Okay, so the expectation is in the thermodynamic limit, any T prime, B prime, any finite T prime, non-zero T prime, B prime will give you the Wigner-Dyson distribution. Wigner-Dyson, that's right.
And the black?
The black is the numerical Russell. Yeah. If this V is 0, I think so. So long as you have T prime, B prime, yes. Okay, but yeah, you have to be careful because yeah, if you take this V, you don't want to take away this V, right? Because then it's quadratic, then it's free fermions, right? It's not. That's no. Then it's super degenerate and so on. So it's something even worse. It's non-interacting fermions. So you see, if you take away this and this term, you have non-interacting fermions. In periodic boundary condition, that's super degenerate. So, but what I'm saying is, if you take this guy, but you keep these two, still, when T prime, B prime are sufficiently large, you're going to go to a Wigner-Dyson distribution. That's right. That's right. That's right. And you know, actually, you know, this is something that I mean, you don't know when you look at this plot. This is a rectangular cavity, but really the size have been, the sides of the rectangle have been taken to be very incommensurate and so on. Otherwise, you get like a delta peak. So it is everywhere, right? I mean, you take harmonic oscillators and so on. So, okay? Good. Right. That's right. Yeah, the Wigner-Dyson distribution, right? You can predict it is the. Yeah, of course, there is the level. Yeah, there is the unfolding process and so on. Yeah. So this is all normalized so that the average level spacing is the same in the entire spectrum. You mean in this model, right? That's right. Right, but this is the unfolding procedure. So actually, you know, the system sizes we can diagonalize nowadays are so large. You go to the middle of the spectrum, you don't even need to do the unfolding. Okay, so but yeah, this is with the unfolding, and you see how well it works. So there was a question there. Right. That's. Yeah, I mean, this is very large. Right? No, you have accidental degeneracies, but this is not, they are not massive numbers. No, these are order 1. So if you tune, no, because it depends how many you have. Okay, so if you have 10 degeneracies in a spectrum that 1 million levels, you don't see it. Okay. But this is, no, but this is not probability 10. You have just 10. Right? So it doesn't affect this. You will not see it. They are there. They are not there. So let me be clear. So if you take this T and V, you can change them, and the levels change, right? And then you can have level crossings. They are not massive. Okay. So you have this delta peak if you have free fermions. Okay. So but. No, but you have them. Still, you have them. No, but you have them. I mean, what we're saying is totally right. There are these dynamics. After, no, these ways to remove them. Right. I mean, maybe you have ways to remove them. That's right. I mean, we didn't remove them here. But you don't see them, Peter. I mean, you don't see them. They look, I mean, you integrate here, right? You get 1. Right, and these are 10,000 level, 100,000. So you just don't have a delta peak. Okay.
There's no contradiction. It's a way of taking limits.
Questions? Other questions? Good. So, okay, good. That's great. So now let me tell you how we are solving that problem exactly. Okay, so how is it that we solve that that problem exactly, the one that I show you of the dynamics of the hardcore bosons? Okay, so these are these hardcore bosons now. So essentially, you see, it looks like a quadratic Hamiltonian. So you have hopping, on-site potentials, right? And then, of course, it's not quadratic because you have this constraint that you cannot have 2 bosons on the same side, right? And that's the reason why you cannot diagonalize this Hamiltonian at this level because of the constraint. But there are these beautiful transformations that you can map the bosons, the hardcore bosons to spin and spins to fermions, do this Jordan-Wigner transformation. So you can map this guy into this Hamiltonian, which you can diagonalize because now it's quadratic. Okay? So now the big problem of this transformation is that it's non-local, right? So you can get all the local properties of the bosons like densities, density-density correlations, all the thermodynamics to be the same as free fermions. But if you are interested in discussing correlation functions and momentum distribution functions, they are going to be different. Okay, and this is where we spend the time. So there is another thing I should tell you at this point, that you see when you do this mapping, this naturally already gives you something that must be conserved in the system, because since this is a quadratic model, non-interacting particles, whatever populations, right, you put into the eigenstates of this single particle Hamiltonian, it cannot change because they are non-interacting. Okay, so later I'm going to use this, that already this tells you that the occupation of the eigenstates, the single particle eigenstates of the free fermionic Hamiltonian, this gives you a natural set of conserved quantities for these hardcore bosons. Okay, so if your system is translational invariant, then these guys are occupation of momentum modes. Okay, like momentum distribution function of the Fermi. That clear? Okay, so just keep that in mind that there are these natural conserved quantities, but they are not extensive. So the real work starts when you try to compute correlations, because now when you go from the spins to the fermions, you get these non-local strings. And the way this is usually solved is using weak theorem. I mean, we decided to use a different approach through Slater determinants that allows to deal with equilibrium and far from equilibrium the same way. And the approach goes under the realization that if you have free fermions and many body states, those are Slater determinants. If you act with exponentials that are bilinear in creation annihilation operators, what you can prove is that you get back a Slater determinant in which you know what this P is. Okay, this is the exponential of that representation of this Hamiltonian, the matrix representation in the single particle basis, and this is a matrix. So we know how to calculate this. And now if you look at these guys, these are bilineals, right? So again, we can act with these guys on this, get a new Slater determinant, and we can create a state, a particle on them, you get a Slater determinant. So essentially what I'm telling you is that everything that you need to do about equilibrium and non-equilibrium now involves contracting Slater determinants. And the contraction of a Slater determinant, you can prove that is a determinant of the product of the two matrices, this piece that you get on the left and the right. Okay, so this is great because you see, this is telling you that now to get this many body somehow this result, which is the one body density matrix in a many body system that is interacting, all you need to do now is just like a polynomial calculation. So it's the determinant of a product of two matrices. Okay, so this scales with the L squared is the size of the lattice and the number of particle cubes. So you can study very large system sizes. You can solve really equilibrium and far from equilibrium for very large system sizes. Okay? I'm sorry, does it still work for what? Yeah. Yeah, I mean, I'm telling you, those are the sizes that I'm going to show you results now. No, these are all dense. And so. Okay. So, what's that? This is only one dimension. Remember, that mapping, everything I've been telling you is in one dimension. For free fermions, it works in any dimensions. As a matter of fact, I learned this from the determinantal quantum Monte Carlo when I was doing in 2 dimensions. So that's right. That's the kind of thing that you use with fermions in higher dimensions. Okay, so good. But now it's an interesting question that you can ask. Okay, well, you have that mapping, right? So you have this underlying fermion. So is there any way in which you could see those fermions? Right? So unremarkably, there is. Okay, so could you measure something in the bosons that will tell you that those fermions are there behind, right? Yes. So, and this was something that we realized back in 2005, and someone else had realized and thought that that was a problem with doing time of flight experiments. So let me tell you what the idea is. So suppose now you have your hardcore boson gas in here, okay, which has this momentum distribution function I showed you before. It's a peak. And you let it expand. So what suddenly realizing, this is what in the early days of ultra-cold quantum gases, is that, this idea of time of flight in which you let it expand and then the density distribution becomes the momentum distribution function doesn't apply in this system, okay, because of interactions. So, okay, so essentially if you let it expand, so what's going to happen is the momentum distribution function is going to change. Now, in this hardcore boson case, it's going to change in a very peculiar way. Remember, I told you that these rapidities become the momenta asymptotical at zero density. So as this becomes more dilute and more dilute so that the bosons don't interact with each other anymore, then the rapidity distribution, which is conserved, will coincide with that momentum distribution. Okay, so let me show you how that happens. So this is now, again, an exact numerical simulation. So, okay, so you see it is expanding, and there you go, it's already 2,000 sites. Someone was asking about the sizes. And you see that it goes in there. Okay, so it's kind of amazing, right? So if you go, this is something that you would not see if you restrict yourself to equilibrium situations. So you will never see this rapidity distribution. But if you let this gas expand, then you see the rapidity distribution in that flat potential. Because what are or conserved are the distribution, the momentum distribution function of the underlying Fermi. Okay? Everyone's, any question about that? Good. So now, okay, so what you can think is, can that be seen experimentally, right, beyond this numerical experiment? And the answer is yes. So, and this is something that we are about to publish. So now, what is measured in the experiment? So let me try to now come back to this time of flight so that you have the picture. So you see, you have these bosons, they are expanding in 1D, right? And then they are interacting. Right? Everyone sees that. So now in the experiments, what they can do is at any time in the expansion, they can turn off the trap. Right? So what happens when you turn off the trap? Those bosons are very confined in the transverse direction, so they expand very quickly, and the interaction energy drops very quickly to zero. So the expansion in the x direction, like in the direction that they were originally expanding, that remains after you've turned off the trap, is non-interacting. So, and then if you let it expand for a long time, then at long times, the position of the atoms will correspond to the initial momentum, right? Because the initial position didn't matter. That's what time of flight means. Okay, so now I'm going to show you what the time of flight of this momentum distribution would look like in an experimental setup like the one that David Weiss has. So this is what would happen. This is what he would measure. You see, C time of flight. Now he takes a picture and he will look at the distribution of the bosons. And this is how many bosons he sees. So these are different times. Okay, so this is nothing but a rewriting of this case, okay, in position put in time, okay? So now this is the numerical calculation. This is the experiment. Okay, so this is the experimental result. And you see it's already pretty amazing, right? Because you see the red line is very similar. The green is similar, already some difference at that level, right? So, but we can do better because we can solve that problem exactly. So we can account for the fact that in the experiments, they don't expand forever. They expand for some finite time. We can also account for essentially the imperfections of the camera and so on. So if I correct this for all I know about these experiments without free parameters, this is what I get in the theory. Okay, so that's an exact theory. Theoretical description of what the experiments have. So now let me just put one-to-one plots here. So this is at zero time, we have a difference. So the experiment is a slightly higher momentum than the theory, and the reason for that is that the theory is done at zero temperature. The experiment has a finite temperature, that's why they have a lower peak. But you see, after a linear expansion, then there are no differences. Okay? So now the other thing that you can do is say like, okay, let me take the longest time and compare the momentum distribution function with this time of flight, with the momentum distribution function of the fermions, which are the rapidity distribution I told you that the system had. And this is the plot now. Okay, so, and now you see that essentially they are almost the same. So you see that indeed the fermions are slightly sharper here. They have some kind of Fermi edge that still hasn't been resolved. But you see that by doing this expansion, they have experimentally seen a momentum distribution function of bosons that is the one that you would have for trapped fermions in equilibrium. Okay? So experimentally, if they are given that momentum distribution function, they wouldn't be able to tell the difference between having fermions in equilibrium in a trap or having this hardcore boson. Okay? So good. So you see that those distributions are real and they can be measured. Okay? Now, for the rest of the talk, I also will need to develop a technique that can do what I showed you before, where pure states and dynamics, essentially thermal equilibrium distribution. So this is something that, that we can do in the grand canonical ensemble. I'm not going to bore you with that. So just believe me that you can use the mapping and you can show that the one body density matrix at finite temperature is just a difference of some determinants with a big bunch of matrices. So, the density evolution, they don't see it in the experiment because that all happens very small. But they could, at the longest time, they could take a picture, and this is something that we are looking at right now. I mean, they can take a picture, but they don't have the resolution to see the profile. No, it is just because that's very small. Okay, this is a very tight, very small thing there, and then you let it expand, it becomes big, and then they can take the pictures. I mean, now people can see those distributions with these atom microscopes, right? But Dave doesn't have that resolution in that experiment, so he has it in another experiment. Okay, other questions? That's right. That's right. You're paying attention. That's right. So this it was in the lattice. So you see the side occupation is like 0.4. So this is a lattice. So it sees that the system is the lattice. Indeed, in the experiments they are in the continuum, and the theory was done in the continuum. I mean, it was a lattice theory in the continuum limit, but you see how well it works. Okay. Okay. Any other question? Good. So then we are ready to do the experiments that we were looking for, which is just now thermalization in these systems. Okay. So good. So let me show you. So I show you that what happens if I put the harmonic trap, and you saw that in the theory things went back and forth. They never equilibrated. Okay. So but in more general situations, so you don't have a harmonic trap, but you have a box. So suppose you have a box, and you let the bosons and look at, so you have a small box that you open a bigger box, and the initial momentum distribution function looks like that, and you let it go, right? So what happens with the density? It levels off. Actually, it becomes like almost homogeneous, right? The kind of thing that you expect in general. So you let particles expand in some box, and then they will become homogeneous. But you see, this is amazing, right? So this is unitary dynamics. Okay, if you look at the momentum distribution function, it's just relaxed. It's sitting there, right? So I don't need to do even time average, nothing. So it is in there, it doesn't move, and I don't remember how many atoms are in here, like maybe of the order of 40 or something like that. So that's incredible, right? So you get unitary dynamics, integrable model, and still these two things equilibrate. So the density becomes homogeneous, the momentum becomes this thing, which we don't know what it is, and we're going to see what it is. So let me show you another case. So in that case, you quite don't know whether that is a thermal equilibrium or not, but in this case, you will not. You will know. So what I do now is I have the same box, and then I put a lattice potential, so that's why the density looks like this, and the momentum look that you see the peak you had at 0, plus the replicas at this lattice momenta. So if you let this guy evolve, and this one, then you don't need to do any statistical mechanics to know that this guy is not thermalizing. You see, so now the density is again becoming homogeneous. If you look at the momentum distribution function, right? So if you have bosons in a box, right? How do you expect the momentum distribution function to be? Just one peak, right? At very high temperature, you expect a Maxwell-Boltzmann distribution. But you see, this guy really remembers, oh, I am coming from that state, and now the momentum distribution function has all these peaks. So there's no way, no hope that you can describe that with any like traditional statistical mechanics, right? Everyone agrees with this. So if you do this experiment, you immediately know this guy is not thermalizing. That's right. With open boundaries, it's a box. Right. So what I did is, from that experiment I showed you, I removed the harmonic trap, which is problematic, and I just put it in a box. No, that's not true, because the momentum distribution, so you see, these are two matrices, right? So you have rho of x, x prime, right? And in momentum, you have the other one, n of p, p prime, right? So indeed, the p, which is p equal p prime, is the Fourier transform of everything in here, but you have x and x prime. And here I am only giving you rho, what I'm showing you there is rho of xx. Okay, so that's what I'm showing you, right? It's just a vector. And I'm showing you in here the rho of xx, and in here the n of pp. Okay, you cannot get one from the other. Okay, you don't have enough information. Other questions? Okay, good. So that's settled. So what is it that we've learned here, right? So we've learned two things, right? I think that are important. The first one is you take an integrable model, okay, take it out of equilibrium, and things equilibrate, right? You look at observables, they become time independent, right? That's the first thing we've learned. And the second one is that whatever that time independent thing is not described by statistical mechanics, at least not traditional statistical mechanics. So let me be more quantitative. So what is it? What would be the statistical mechanics description? So question, huh? That's right. That's what I'm going to do right now. Right. That's what I'm about to do. Okay, good. So you are ahead of me. So what is it that you could do naively? This statistical mechanics, you have an initial, you have a state, and it's unitary evolution, so the energy is conserved. So if you want to do like a statistical mechanics, right, what you could do is just say like, okay, I'm going to use an ensemble, like a grand canonical ensemble, and that goes back to what I told you before. The exact solution that I can get in polynomial time is for the grand canonical ensemble. So even though that box has a fixed particle number, now I'm going to compare these to a grand canonical ensembles. In the thermodynamic limit, all ensembles should be equivalent for these observables, okay? So you have a grand canonical ensemble, but you have two things that you don't know, mu and t, and the way you fix them is that, okay, you want the energy of that ensemble to be the energy of your state and the number of particles to be the number of particles of your state. Okay, that's how you go from that pure state now to the statistical mechanics description. And if you do that for the first case, the box, this is what I show you. This is now the zero momentum occupation, and this is what you saw. It goes down, oscillate, and then it becomes constant. So this is the constant in time, right? And this is what statistical mechanics would predict. Now you could say, well, but these are small systems. How do you know the ensembles are equivalent? What I'm showing you here is now after relaxation in here at long times, for two different number of particles, right? Properly taking the thermodynamic limit property because you have to take care of the traps. But the point is, if I do 30 particles and 15 particles, you see that the quantum mechanics doesn't change and the statistical mechanics doesn't change. Okay, so the fact that these two guys are different is not a finite size effect. Okay, so how can we do better, right? And that's what was said before. Well, we have to remember that we have all these conserved quantities, and we should take them into account. So if you essentially maximize the entropy of the conserved quantities, you get this generalized Gibbs ensemble. Well, now the big difference between this guy and this guy is that in here, you have order one number of parameters that you need to fit. In here, you have order L, so it's as many as lattice sites your system has, right? So that's very different. So this guy diverges in the thermodynamic limit, so the number, right? So, okay, so that's what you need to do, and you need to now find these lambdas, and this lambda you feed by saying, well, the expectation value of your conserved quantity in the ensemble has to be the same as in the time evolving state, and you can get analytically for this system that is mappable to free fermions that this is the expression. So you see it's even easier than with a grand canonical ensemble because you get this analytically, you don't need to just fit it. And if you do that, then you get a perfect agreement, right? So you don't see the difference between the two, right? And you, of course, can say, well, but this is almost featureless. What happened for the other? Well, for the one with the many peaks, Of course, the GGE tells you that this is flat, and this is what will happen at very long times in the thermodynamic limit in the density, but already in the momentum distribution function, you can see it. Mario? That's right. Right. Not in this picture, and that's being studied. So not these conserved quantities that I'm taking, but you can rewrite and you can have extensive now conserved quantities like energy and currents and so on. And in those ones, you can really somehow truncate, and this is what is known as truncated GG. Okay, and you can ask Mauricio. Right. Yeah, that's right. Yeah, I mean, so I'm going to somehow touch upon that later. So you see, an interesting thing is that the density is the same as for free fermions. This momentum distribution function is somehow having like the interactions inside, that long mapping that you have, okay? But that's a good point. So that the density is the same as happened for free fermions, but the momentum not, is different. Okay, other questions? Okay, good. So right, so is it clear? So what is it that I have now? We've learned a third thing. And the third thing is that we can describe observables in after equilibration using those GGs, right? And now you can ask the next question, is that trivial? So is it trivial that, is it obvious? I mean, does it follow that if you put this conserved quantity, this must be the case? And let me show you that that's not the case. So it takes a leap there of faith to see that that is the same. So now what you can go is you go back to the many body picture, okay, and you are thinking now that you have an initial state. It's not an state of your many body Hamiltonian, right? Because that hardcore boson Hamiltonian is many body, even though you map it to a single body one, right? And then you evolve things, okay? So and you know the technology, right? So the energy is conserved. Observables evolve because these wave functions evolve. This is the way it evolved. And this is what I did. So what I did is very brutal because I said after some time T star is something that I can describe with order L numbers, this extensive number of rapidities, right? But we also know how to do quantum mechanics, right? So we know that this guy, we can obtain it by writing this guy in terms of the eigenstates of the many-body Hamiltonian, right? So you can plug this in here, this in there, and you get this guy. So important thing is these are the matrix element of the observable in the many-body eigenstates, right? That's what quantum mechanics tells you, right? And now, of course, this depends on time, but if you say that after some T star, this is true, or the system relaxes, well, then, I mean, you can blindly just take the infinite time average is going to be dominated by this guy, right? And that infinite time average, and here you see the question mark, I'm going to tell you why. So if you don't have degeneracies, and that's back to Peter's question, so if you don't have degeneracies, which is all, I mean, generally the case for quantum chaotic systems, is mostly the case for the interacting ones, but this is a mappable to non-interacting ones, so that's why the question mark. If you don't have degeneracies, the infinite time average, what it does, it kills the contribution from the oscillating term, so you get something that is diagonal, okay? Now, for this box that I have, this is not a periodic system, this is still true that you don't have massive degeneracies that would kill this equality. Okay? Not the case if you have translational invariance and so on. But what I'm telling you is for free particles, you have to be careful with this. I was careful, and I can show that this guy is relaxing to this guy. Okay? But what is the important message that I want you to take from this? That really the quantum mechanics description involves exponentially many numbers, right? All the projections, right, of your initial state onto the eigenstate of the many-body Hamiltonian, right? While here I am taking only polynomially large, right? So it's not a given that if you use a generalized Gibbs ensemble, this is going to be equal to this. Okay? So is that clear? No. That's the important thing. That's what we call the diagonal ensemble. That trivially always works. Okay, so that's very important. So what you're saying is, I mean, you could think of this also as a generalized Gibbs ensemble in which now the occupation of the many-body states are the ones that you are given by your initial state. But you see, you can use that description whether the system is integral or not, right? And this is just, there is no statistical mechanics in there. It's just quantum mechanics. Yeah, to think of this as a generalized Gibbs ensemble is a bit of, overdoing it. There is no statistical mechanics in that, right? It's just quantum mechanics. So the generalized Gibbs, there is a statistical mechanics because of this, because now you got only polynomial. So this in general, it can be different from the quantum mechanics prediction. What you're saying is it's just a quantum mechanics prediction. Okay. Other question, huh? Right. That's right. That's right. And I'm going to tell, I mean, that's right. I'm not going to discuss that. But then what happens is something that is called eigenstate thermalization. And what I'm be telling you now is the generalized version of that. And then tomorrow I'm going to mention this eigenstate thermalization. But indeed, then it's a bigger problem, right, for the non-integrable one, because then you have order one. That's right. That's right. That's right. No, right. Yeah, this is another, and this is a big problem. I think that is a big problem that is not solved. I mean, what is the equilibration time and so on? But what helps you is indeed these guys are exponentially small, but they are exponentially close. But these guys are also exponentially small. So that's why you wait order one and the whole thing is gone actually. But that's a very good question. Something that is open. What is this equilibration time? Okay. Other questions? Okay, that's great. So you see, this is non-trivial, and then comes something that something that we've been like thinking about since this GGE, and also related to quantum chaotic systems. Right. That's right. It will be operator. That's right. That's right. Yeah. That's right. And the other guy is a polynomial, very slow. That's right. Yeah. This star depends on the operators. Okay. Good. So now what is it that you could do? So what you could do is like, well, but maybe because of some miracle, right? When I build this ensemble, I am effectively sampling these states, right? You can believe in miracles. You can say, well, maybe you are doing the job by doing this, right? So just build that ensemble, and it's going to sample precisely the states that had a finite overlap with the initial state, right? So how do you test for that? What you can do is compute the entropy of that diagonal ensemble. So this is this ensembling here, right? It will tell you, it will give you an idea of the number of states involved and the entropy of the GGE, right? And that's something that we did with Tolia Polkovnikov and Lea Santos many years ago. And this is what you find if you do that. And these were quenches in a super lattice potential. So you find that both the diagonal ensemble and the GGE entropies grow with L, so linearly. That's great. They are extensive. That's good. So it means that both ensembles are sampling exponentially many states, but the slopes were different, right? So the entropies of the two are different. So, and you see the GGE is higher than the diagonal. So this guy is sampling exponentially many more states than the diagonal ensemble, right? That's pretty amazing. So I'm just telling you, if I look at the observables, I get the same result, even though the two ensembles have exponentially different number of states. So it turns out that for the transverse Felicing model, translational invariant, you can prove that the difference between the two is a factor of 2. Okay, and there is a quasi-particle picture understanding of this, about quasi-particles being created in pairs when you do the quenches, and the GGE being blind to that. Okay, so this factor of 2 is even, you see, this is a mappable, the theory that is mappable to non-interacting theory, even more remarkable, this is still true in the spin 1/2 XXX chain. And this was something that we found first numerically with Pasquale, and then later that year, with Vincenzo, they proved that that must be the case. So even for interacting integrable models, this is true. You take a pure state, you do the quench, one entropy is twice the other.
Initial condition? Initial
No,
state?
it doesn't depend on the initial condition. It's just you take a quench, it's a pure state. That's the important thing, right? So you take the pure state and then you do the quench and you get this factor of 2. Right, but this is, you have a translational invariant and then you do a quench. How do you mean? So but for many states, even in the transfer Felicity model.
If you take just in energy eigenstate, then SDE is 0.
No, but there is a quench, of course. I mean, I'm starting from the point that there is a quench. So, and now the DE, I am starting from the fact that now the DE is not a pure state, right? You see, because if you have a quench, the DE now is a mixed state. Okay, so. Right. Right, that's right. I mean, no, but this, you will have to break like translational symmetry from your initial state. And you can break it. Right. So, but and let me just be clear about this, right? So I have started from the fact that this 2 is non-universal. Okay. So I started from this fact. In here, it was not 2. It's not universal. For these translational invariant quenches in which you start with the ground state on one side of the ferro and then you go to the para, then you can show that it's 2. Okay, so or maybe there are states that yeah. Okay, so that's what is shown there, and then there is an equivalent generalization for the interacting integrable. Okay, so why does it work? Right? If you are sampling exponentially many different states in one and the other one, and this was something we looked at some time ago, and it goes on the idea of this generalized eigenstate thermalization. So, and the bottom line of that is that if you have states that have similar distribution of these conserved quantities, local operators will look the same. Okay? So that's and then what you do with the GGE is precisely do that, right? You sample states that have the same distribution as your diagonal ensemble, even though you are putting more states. Okay, so, and actually this is what is behind these generalized thermodynamic Bethe-Ansatz approaches and this saddle point approximation, the way in which people find dynamics at long times using Bethe-Ansatz. So somehow that is behind that. So if that would break, then all these Bethe-Ansatz approaches would break. Okay, so now let me show you that this actually works. So and, I'm going to show you a picture and then an analytic result. So you can now do the following, right? So you start with some, you do a quench. Again, as I was saying, this is now in the transfer field easy model. You take it in the paramagnetic and go to the ferro or vice versa. So I don't remember which quench was this in particular. So now you look at the this next nearest neighbor CSC correlation. Okay, now you look at the expectation value of that in the eigenstate of the Hamiltonian. Okay, you build your eigenstate, compute that, you plot it as a function of the energy of the eigenstate properly normalized, and you get this black thing that you have here, right? So, and you see, and you increase the system size, you get this black thing, it doesn't shrink. That's essentially telling you that you don't have eigenstate thermalization. I will show you what happens in a quantum chaotic system. But the interesting thing is now you look at which are the eigenstates from this spectrum that contribute to that diagonal ensemble. And you see they are in here, right? So you increase system size in here, but you see as you increase system size, you see that they are peaked like at some point that has both like kind of a fixed energy and a fixed value in there. So you see that almost all the eigenstates that enter in that diagonal ensemble have the same expectation value of this operator. Is that clear? So, okay. So everyone sees what I'm doing. I'm really taking the full spectrum of the quantum Hamiltonian, looking at this, the expectation value of this operator, right? And then seeing that all the eigenstates that have a non-zero overlap with the initial state have this expectation value of that correlator, okay? So you can do now the same for the GGE, right? And what happens for the GGE, you see now I can do half the system size because I have to build exponentially more states. You see the picture is the same. And actually what you see is that the point at which they are building up is exactly the same. Okay, so what is the picture that emerges from this? Is like you are building an ensemble that have more states than you originally had, but that ensemble is sampling states that have the same expectation value of the observables as the state that you have originally overlapped with your initial state. Okay, is that clear? So in here it's just a picture, right? So if you look at the variance, now this you can calculate analytically for quenches. You see this is what you have to compute, and what you find in these quenches is again the ratio of the variance of the diagonal with the GG is 2, similar to that factor of 2 that we saw in the entropies, but each of them scales with 1 over square root of L. So going back to which quenches, so for example, these ones are quenches in which you start with chain naught and quench to H naught smaller than 1, larger than 1, and vice versa. And this is the analytic result for the variance, and you see that goes to 1 over L. Okay, so the variance vanishes as you go to the thermodynamic limit. Okay, so all the eigenstates that you get, the overwhelming majority of them have the same expectation value of this SZSE. Okay, so and with that, I mean, I have essentially, and then we have 20 minutes. That's perfect. So we have a lot of time to discuss. So I think I have essentially walked you through all the ingredients somehow that you need to think about this generalized or thermalization in integrable systems. Okay, so essentially what I've like shown you is that you have these integrable systems that you take them out of equilibrium, pure state, evolve unitarily. There is equilibration. You can describe the equilibrium state with these GGEs, which maximize the entropy, right? And I have justified that these GGEs work because essentially they sample states that even though they are not the same number of states that you sample with your initial state, they have the same expectation values of observables as the one that you sample. Okay? So that's the picture. So questions about this, because now then I'm gonna kind of on purpose confuse you a bit just so that you see that you have to be careful with these things. So questions, okay, there's a question there. More, that's right. Right, I mean, in this quasi-particle picture, you could say you could have the K and minus K, but you could sample minus Ks, like 2 quasi-particles minus K and 2 quasi-particles plus K, that still the average gives you 0, and then that will give you, in one case you have 2 states, and the other one you will have 4. Okay. How do you mean? Smaller, no, what I said was that the overwhelming majority of the state contributing, which are exponentially many, right? They all have the same expectation value of oh, this is the GGE entropy. I mean, that's, in here is the GGE and here is the diagonal. The other ones are subdominant, they are much smaller. Okay, so you see what I'm saying? So what I'm saying is the entropy is given by those states in here. So all the other states which you see as you increase system size, they are collapsing into there. Whatever is not exactly that is a negligible part, the vanishing fraction. This is half, of this, right? Right. The number of states here is actually the same as here just because the system size is half. But if you put the same system size, one is twice the other. It's just what this number is telling you, right? Like this number in here. Okay? But you see, I'm just telling you that this entropy, those states are the states that have the same expectation values of the observer. These are these guys. And you see it in here, Rajiv, because the variance, I'm showing that it vanishes, right, as 1 over L. You see it in here. Right? So it's increasingly peak, and then in the thermodynamic limit, essentially, they are all there. Okay? Other questions? You mean powers or products of these I's that I put here for the free fermions, right? Yeah, I think that there being work showing that with these I's you exhaust everything. The other ones don't give you anything. But indeed, if you have particular initial states in which you break like translational symmetry and you have degeneracies and so on, then things become tricky. And I think Mauricio has some work on that, on which are the conserved quantities that you need to take to build the GG. But this is in systems in which you have essentially degeneracies. Okay, as far as I understand, right, Mauricio? So in this case that I don't have degeneracy, these conserved quantities exhaust so products of them give you nothing. The same way that if you take a quantum chaotic system, right, you usually take into account the energy, right? But you could also consider energy variance and higher, right, powers of H. They don't add anything. Okay, is that clear? The number of conserved quantities, right, yeah, it's not special. As a matter of fact, for interacting integrable models, then there are families, and it's a whole story like quasi-locals and so on. But in here, for this mappable to free fermions, in the absence of degeneracies, it's just natural and is what exhausts everything.
Marcos, I think you are not very careful about explaining what the initial state was. So you didn't say what the quench was.
Right. So no, it is in here. So that's what I say. I start with the ground state for H naught, like the H in the Hamiltonian. So I should have put the transfer field is in model Hamiltonian here. You see, everything is, there is only one parameter, H, right? And the initial H is what I call H naught. And I take it to either be smaller than 1 or greater than 1. And then the quench is I evolve with H greater or smaller than 1. So
you start from the ground state of
I start with the ground state, that's right, in this case. But we've looked also at, you can also do excited state. Okay, other questions? Okay, good. So now there is something that I find interesting that I want to address, which is this picture of, well, you really have to take a look at a little piece of the system, the reduced density matrix in space for all this thermalization to make sense. And I would like to argue that that's not in general true. You could think of reduced density matrix in a different picture. So trace out n-1 particle and now take out the one body density matrix in the entire system. So it's not something local, but still has n-1 degrees of freedom that can allow this to thermalize. So, and there is a place where you are going to see a big difference between non-interacting particles and hardcore particles or hardcore anyons. So let me show you that. So one thing that is trivial for free particles is that the time average one particle density matrix is the GG. And that's by construction, right? So the time evolving density matrix written in the eigenstate of the Hamiltonian has this form. And if you don't have single particle degeneracies, which is the case I was telling you for the box, if you do this time average, it kills the off diagonal, so you get something like this, and that's what the GGE is constructed to be exactly this. Okay, that's trivial, no finite size effects, nothing. So you take free fermions, the GGE is the exact description of the time average. But now what you can ask is, if I go at any single time and find the distance between the density matrix and the average or the GGE, what is that? Well, it turns out that that doesn't change. That are conserved quantities. Because, so this is the trace distance, that's the definition. The normalization here has an n because the trace of this one body density matrix has the number of particles, okay? So you may be used to something that is 1/2. There is a 1/2n because the trace of sigma is n. Okay, so essentially now you see what happens for free particles. So actually for free particles, the one particle density matrix evolves unitarily, right? Because they are free particles. So, and the GGE is diagonal. So that means that the trace distance between at any time and the GGE, you can immediately see that is a conserved quantity. Okay, so what this is telling you is that you take free fermions, the time average of the one particle density matrix is the GGE. At each time, the density matrix is completely different from the GGE. Okay, that's pretty amazing. That's not to say that there are no one particle operators that are GGE. I show you that the density is GGE. But the density matrix, the one particle density matrix, is not GGE. So is that clear? So now what you could think is like, oh, wait, and if this is true, what happens with bosons, hardcore bosons? So like motivated by these questions, so what we did in this paper is, well, let's try to study a model that interpolates between hardcore bosons and free fermions. And those are these hardcore anyons, right? Because you see, you can have this theta, and if you change it between 0 and pi, you are going to change between those two limits, and you can do it continuously. So, okay, we went there and did similar quenches to that original paper I told you. You have a box, and then we open it into a larger box. This is the quench. Now that Hal wanted to be very precise with the, so we start with a box, a small box, and open it in another box that is larger. We start with the ground state, and we go from 2n, the box has size 2 times the number of particles, to 4n. That's what we do. So this is how the initial momentum distribution functions look like depending on theta, right? Which we change from 0 to pi. And you see, you go from fermions with the Fermi edge to hardcore bosons through a peak that moves, right? So these are the GGEs for the momentum distribution function. So you get the fermions, still have some Fermi edge, and the hardcore bosons is what I showed you before. You remember that smooth curve. Okay? So now let's ask the questions, okay? So let's take a look at distances. So now you see, I've done the quench. This is the initial state, that's the final GGE. So what I want to do now is at each time, let me have a measure here that tells me how different is the momentum distribution function at each time from the GGE, right? So that momentum distribution function I integrate over K, density I sum over site occupation. Okay, so now I have 3 measures to compare these things. I can compare how different the momenta are, how different the density distribution are, and how different the density matrices are, right? These are the 3 things. So now let me show you what happens for free fermions so that you see clearly here. I told you that the trace distance doesn't change, so better the numerics give that, and that's what it gives. If you look at the momentum distribution function, right, and now you see there are some size dependence and so, but at long times, you see that essentially this number is different from 0 and is not decreasing. So this is telling you that the momentum distribution function is not equilibrating, right? Because this is always different from this. Everyone sees that? Because you get a number and you see the oscillation decrease with increasing system size. On the other hand, look at this, free fermions again, but instead of looking at momentum, I look at site occupation. You see the picture is completely different because I get these oscillations, but the average at long time is decreasing with system size. Everyone sees that? So what is it that I'm telling you here? That if you take free fermions, the density equilibrates, the momentum distribution function doesn't equilibrate, and of course, you know that there are observables that don't equilibrate, one body observable, because the trace distance is not zero. Okay, everyone agrees with that? Questions about that? What I'm gonna do next is then turn on the theta. And this is the picture for any theta. So as I increase theta, small, so you see both now, the momentum distribution function. So let me tell you again, so for all values of theta, this result stands, right? Because you map the hardcore anyons to fermions, so the density of the hardcore anyons is always this. That doesn't change. So that's why in here I only show you momentum and trace distances. And what you see is so long as theta is non-zero, you see as you increase system size, that average decreases, okay? And the trace distance also decreases. Okay, you see that? So now what we can do is take a big bunch of thetas and then plot, right? Because ultimately this tells you everything, right? If this is zero, all one particle observables that you can come up with must be GGE, right? Everyone agrees with this. The two matrices are identical. There is no one body observable that is not going to do that. And this is what you see as you do this trace distance as a function of theta for different system sizes. So small systems, you see, you don't see the effect of theta for a small theta, but then as you increase system size, you see at any value of theta, things decrease. Everyone sees that? So what is the picture that naively you could see, you could think emerges here? In the thermodynamic limit, this is non-zero and everything else is zero. Would everyone agree with me that that's a reasonable conclusion looking at that data? Right? So let me plot that data differently. Let me take a theta and then plot a function of L. So that's what is shown here. So this is the clearest case, right? In which you go to the hardcore limit, and then if you plot as a function of L, then it's a perfect power law, it's 1 over square root of L. So as you decrease theta, you see that what happens is that it takes some time for you to get into that power law regime, right? But the expectation is for very large system, no matter what theta is, so long as it's not exactly zero, it will go to zero. Okay, everyone sees that? So, and then this is now the important conclusion that we have, right? So you see, so long as you don't have the free fermionic limit, so that your bosons or the hardcore bosons or hardcore anyons are really interacting, so the one body observables, all of them, not only like density or momentum, whichever you could come up with, will equilibrate. As a matter of fact, the statement is that the one body density matrix in the entire system, right, is GG. Yeah, all this is done by the mapping, that's right. It's like kind of a, yeah, that's right. This is just a generalization with this theta. That's right. So all the calculations are done with that mapping. So it's exactly the same technique I showed you before, just taking into account that is in here is not pi, but it's theta. Okay? But that's why, because I get asked often, like, I mean, local versus few body, right? So the one body density matrix is non-local, right? It lives in the entire system, but it's few body. Right? And then what I'm showing you here is that there is this few body observable that equilibrates to the GG. And the same will happen when you have non-integrable system, that it will thermalize. Okay, and this is important because the experiments I show you, they look at momentum distribution functions, right? And as I was asked before, the momentum distribution functions are the Fourier transform of the one body density matrix. So essentially the momentum distribution function is few body is actually one body, right? But it's non-local. Okay? So, and that's the picture that somehow I think often is given the impression that really you have to take a small system into a big system. It has in space, right? Oh, the other part allows you to thermalize. So it's more general than that. You can take something that lives in the entire system and other degrees of freedom allows you to thermalize. There is none. It's right, that's right. Okay. That's a good point. That's right. So for local observables, as the density, you see there is no distinction. Okay, that's right. So if you look at guys like this, they will tell the difference between truly non-interacting and essentially interacting mappable to non-interacting. Okay, so in that sense, that is also important. Another message I want you to take from here is that hardcore boson or like transverse field in model, these are not free fermions. Okay, they are mappable to free fermions, but there are things that are different, and this is one of them, because the one particle density matrix of the free fermions is evolved unitarily, not for the hardcore bosons. Okay, so and with that, I'm going to stop. That's great. It's right on time. You see. So good. So let me just summarize. Okay, I've summarized like 3 times, but we're about to summarize again. So what I have shown you is that few body observable in integrable systems, you know, evolving unitarily, pure systems essentially equilibrate, and of course there are recurrences, but most of the time the systems are in this equilibrated state. Okay. So the other thing I showed you is after equilibrations, observables can be described by these generalized Gibbs ensembles, which take into account all the conserved quantities. And the thing to keep in mind now, going back to questions that I was asked, the number of constraints in them usually increase polynomially, while the system, the Hilbert space increases exponentially. So in that sense, there is some meaningful statistical mechanics being done, as opposed to that diagonal ensemble that there is none. And the other thing that I showed you is that this GGE works ultimately because there is this underlying generalized eigenstate thermalization, which tells you that the expectation values of body operators in eigenstates that have similar distributions of the conserved quantities are the same. Okay, so and I show you result for the transfer field in model that you have something that is grand canonical. For a microcanonical description, you can see that actually the original paper we did it for a system that particle number conservation. So, and the final thing was that I showed you that if you take hardcore anyons, right, which interpolate between hardcore bosons and free fermions, the entire one-body density matrix equilibrates to the GGE prediction, except for the free fermions, because in that case, the evolution of the one-body density matrix is unitary. And what I told you is that the effective bath that is provided by the other particles makes that relaxation possible, even though I didn't trace out any spatial domain in the system. And that's it. So let me thank my collaborators from many years. Some of them are not with us anymore, and then the support of these funding agencies. And thank you for your attention.
Okay, thank you very much. So any question, comments?
So in the experiments, when they measured the, let's say, the density profile, so they start from an initial state, and then at some time they just take a.
They measure the momentum distribution function, but
also the density profile, right?
They don't quite, they can. I mean, I think in the original paper they did in this, in the TG paper, in the later one. But in these cases, right, so what they do is they take a picture. Indeed, they look at density at long times, but these are not the density profiles inside the tubes. Okay? So that is important. So let me repeat the procedure to you. So they have the 2-dimensional optical lattice, right? And they have a trap, right? So they turn off the trap and let the boson expand in 1 dimension, right? They don't measure there. They turn off the lattice, and now the bosons expand in all directions. And then after some time, they take a picture from above, and they just get the distribution along X. Okay, so it's a 3-dimensional expansion, the one that they use to take the picture. It's a confusing thing, and that is all like done in the calculation that leads to this. So we have the expansion in the tubes, we do exactly that, and then we also do the expansion in 3 dimensions and integrate to get the 1-dimensional density. That's right. That's right. even each curve here is like an average over few experiments, so maybe a order of 5. Okay, but you see they have this control in which they can prepare very close the initial state, and then they let it go like 5 times, and then they average over 5 shots to get each line in here. Okay, and each shot is already an average over gazillion, actually of the order of 10,000 tubes. Okay, so there is a question over there in the back. Yeah. Well, actually, even that 1 over square root of L, as far as I know, is not understood analytically. So there are some papers by Paolo Zanardi and others for free fermionic models, some bounds for which have this form. But once you put all these non-local things that go into those one particle correlations in the hardcore anyons, then there is nothing. I mean, yeah. So that's right. So this is a numerical observation. Okay.
Hey, any other questions?
That's right, but I motivated it, right? So that what I show is if you have, okay, well, okay, go ahead. So not both give the same result, and that was that's actually some work that that I was involved in. So the quench action is really, and that's why this is what I had in mind when I said this. This is what is behind. This is what is discussed in that paper, right? So I mean, the quench action, you could think of it as the exact solution, okay, under some assumptions. I don't know. Could you agree with that, Mauricio? Like the it's okay. So yeah. So I would say, you see, the quench action is kind of the diagonal ensemble result under some assumptions. So there is some Sadler's point approximation. But oh, okay, but an A is there, so right. Right. You see, when you sum all the quasi-local conserved quantities and so on, that's right. Right. But right, but let me just say something. I mean, definitely in the quench action, there is this generalized eigenstate thermalization at play behind everything, right? Right. So, which is somehow in the Bethe ansatz. So that's right. Right. Like a generalized ETH, right? Exactly. Okay, good. But Mauricio. Right. Right.
Okay. Yeah. Yeah. Okay. Let's look for the talk. So I think this is a good point to stop and go to coffee. So let's thank Marcos.